Welcome to the Centre for Print Research and the University of the West of England. My name's Andy Johnson and I'm the Senior Business Development Manager for the Centre. And I'd like just to give you a bit of an insight as to some of the things that we do at the Centre in the form of print research and the areas that we're involved in. So the Centre is based at the French campus, or at least primarily based at the French campus. We also have a small section based at our Bower Ashton campus, or city campus, where we run our MA printmaking course. But the Centre itself has new buildings at French, and we moved here in July last year. And this is our building that you can see here. And this used to be the old HP laboratories, and that we've now taken that over. Founded in 1998, originally as the Centre for Fine Print Research, the focus was primarily on traditional printing techniques. However, as in 2019, we were awarded with a substantial grant of 7.8 million. The Centre has somewhat expanded and developed since then and has now run into several different themes through print research. We cover areas such as digital manufacturing and hybrid and additive and subtractive technologies. To give you some examples of the sort of things that we're involved in here. We did a project for UNESCO around working with museums to how visually impaired people could experience museums through touch. So what we did here was to create models of famous buildings or paintings, and these had sensors built into them. And as you touched the object, what would happen would be that feedback could come through a mobile phone, letting the user know what they were experiencing, what they were viewing. Imagine, if you will, you're stood in front of the Clifton Suspension Bridge and you're trying to describe to somebody who's blind what they're looking at, what they're seeing. This enables somebody to fully experience that experience. We also work very much within the ceramics industry, and we are developing tools for ceramic extrusion that could be used within the building industry, effectively creating 3D printed ceramics. This could be used on the fascia of a building or to produce things like bricks. A lot of buildings, ceramics are a major part. You wouldn't think of it, but if you think of an average house with fascias, roof tiles, they're all ceramics. Another area that we're involved in is in creating surgical simulation devices. Now, oddly enough, when a trainee surgeon arrives at the hospital, they don't seem to like them going in and experimenting by cutting into bodies without having a bit of practice first. Can't understand why. So we produce again, devices that enable surgeons to practice, that have the feel and the look of the real thing. So when you pick up the flesh, you're cutting into it, it creates the same effect. And even right down to the sound effects that the organs make. This was particularly designed for laparoscopic bile duct surgery. We also work with companies in developing areas such as again, different knowledge transfer of information to companies, known as a knowledge transfer partnership. And here we have a PhD student that works with a company to develop a project or to develop an idea, and that information in turn is passed on to that company and enables them to learn new techniques or to look in new directions. We work very much within the historic museum side of things, looking at printing and imaging and reappraising the past. This was a project that we did last year, which was to scan a Canaletto painting. And we do this with a very sophisticated 3D scanner that enables us to develop very, very accurate representations of the original painting, but also for art historians to be able to view the texture of that painting, which can help them in discovering how it was originally developed, and more importantly, how it, if there are any forgeries or anything along that line that can be put together. We also work with a mixture of different artists in developing new techniques. For example, we run a lot of courses that are focused around the traditional printing areas. We run the Bristol Art Books exhibition each year, known as BABE. It's held at the Arnolfini. We host an international printmaking conference that we're holding this September, and this will bring in artists and printers from all over the world to Bristol to discuss print techniques. And of course, as I mentioned earlier, we run the multidisciplinary MA printmaking course at Bowyer Ashton. We're also looking at new materials and more towards sustainable technologies. And we'll be talking much more of this in a moment with Shaila. But here we're working with products like graphene to look at vital signs monitoring for COVID-19. We're looking at areas such as man-made crystals, and we actually grow our own crystals. And we're looking at ways of making antimicrobial packaging for the food industry using 3D technologies. So as you can see, we have a very varied scope of different research products that we do here at the centre. So now I'd like to hand you across to Dr Shaila Afroj and Marzia Dulal. So Shaila is one of our senior research fellows, and Marzia is a PhD researcher that we have with us at the moment through the Commonwealth Scholarship Commission. So Shaila, if I can hand across to you.
Yeah, thank you very much. Thanks for a lovely introduction. So I'm Dr. Shaila Afroj. I'm a senior research fellow at CFPR. So that's my very formal job title. But in a simple word, I'm a material scientist. So the reason I'm a scientist now is actually this person. Can you, Andy, please show? So this is Professor Shonku. This is a character by Satyajit Ray. So he's a mad scientist. You can see, like, do crazy things. And I was so fascinated by reading all his series that I really wanted to be a mad scientist. But although I loved science, science didn't really love me much. So I was more like a very average student in my school life and college life. And then I did my undergraduate in textile technology and science, and I worked around in the same area. Then I did my master's in strategic fashion management, so I didn't really enjoy it much. And then when I got a fully funded PhD scholarship, that was a very prestigious one, to do my PhD at University of Manchester. That was my golden time in my career, I would say. There, I got to see some mad scientists like Professor Shonku. They were Sir Professor Kostya Novoselov and Sir Andre Geim. Can you show the next slide, please, Andy? So these are the two guys who really inspired me and showed how the mad scientists look like. So they won the Nobel Prize in 2010 in physics for isolating graphene for the first time. And after meeting them, I realized that I'm a scientist, but not really a mad one, unfortunately. So Why I call them mad scientists? Because they, like, apart from their day-to-day research activities, they always kept a time separate for adventurous experiments, or you can say curiosity-driven experiments. So they used to call it Friday night experience. So every Friday night, the whole group can do something that's a bit of not within their area really. So something that's crazy things that will probably not work out really, and if it works out, that will be really fascinating. So they always kept doing it, and out of from Andre Geim's laboratory, out of 24 of Friday night experiment, actually 3 of them were successful. They were really hit. So one was the levitating frog. So he made a magnetic area in the water, and how a frog can float, and he got a Nobel Prize, Ig Nobel Prize in 2000 for that. And the second one was gecko tape, so that mimics how the adhesiveness, mimicking how gecko clings with the adhesiveness of his hairy feet. And the third one was isolation of graphene. So the tool they actually used for isolation of graphene is really simple. It's Scotch tape and pencil. And they really never worked before in the area of carbon thing. For both of them, it was really new area. And actually, the invention started when Andre Geim asked one of his PhD students called the Jiang to exfoliate. So he gave him a piece of graphite. I've sent you one. Probably you can see how it looks like. So approximate same size of graphite was given to the Jiang, and he gave him a very fancy machine to make it thinner and thinner and make it as thin as possible the Jiang can make. And he did it, and really what happened that he actually made it almost like a dust. But very fortunately, the same lab was using some microscopy called STM for looking into graphite. And for preparing the sample for this experiment, they used to use sellotape to get rid of the contamination from the graphite piece, and then just throw it away in the bin. So that time, Costi actually picked it up from the bin, that piece of sellotape, and he looked it under the microscope. And then he realized actually the sellotape contains some graphite that is finer than what Da Jiang has made already. So I can show you. I've sent you some pencils and sellotape. You can probably repeat so the pencil is made of graphite. So as I'm making scribbles, I'm actually putting graphite on the paper. And as I stick to the sellotape and lift it off, you can see I've got some graphites here. I can show you with my tiny microscope here what I can see. Sorry. So if I hold it here, that's what's in my sample now. So these are some graphites what I got on my sellotape. And so these are still quite few layer thickness. If I stick it and pull it back, stick it and pull it back, it is almost like a exfoliating. You are making it thinner and thinner and thinner and thinner that way. And as you keep repeating the process, you actually end up with some graphene flakes, which is monolayer of graphite. And that's what they did really. And see, you can see some of them are very, I'll just focus it, some of them are very almost like transparent. Those are probably graphene flakes. So what they did some, like to make it a little bit fancy, because it doesn't look like very scientific, like you have a pencil and a sellotape. So they swapped with some other tapes, and they tried it again, and they made some nanoscale devices with it, and they did a bit of characterization. And then they realized this graphene, what they've made, this is really not actually graphene, but it is few layer thickness, and it shows some incredible properties, and that was their eureka moment. And yeah, that was it. Then they, after a few, like for a longer time, more research, they prepared a manuscript for submitting in Nature, and it got rejected twice, unfortunately. And one of the reviewers said actually that it doesn't have enough scientific background. So finally, they published that paper in 2004 in Nature, and that was the announcement of isolation of graphene for the first time. And that made it was all over the media and made a big storm everywhere. And then finally in 2010 they got their Nobel Prize for inventing isolating graphene for the first time. So that's how all of it happened. And so you can see, like, the actually Gaim said, like, accidents are really important in science, and accidents doesn't really happen accidentally. You just sometimes have to create an environment to create the possibilities of the accidents to happen, and that's the difference between good scientists and bad scientists. So yeah, these are important. And yeah, if you have made some of your own graphene, you can have a look. If you have a microscope, that would be good. So what graphene is actually, I've got a set of cards here. So if you think that's a piece of graphite, something like that I've sent you, or you can say like the lid of the pencil. So if I can exfoliate it, and I end up with a layer which is 1 atom thickness, that is graphene. So when graphite becomes 1 atom thickness and become graphene, that shows some incredible properties, and that's what we want to get. Andy, can I have the next slide, please? So you can see how thin they are, like from the AFM, like we do, like after making the graphene, then we check how thick it is, then we can identify if it's graphene or monolayer graphene or bilayer graphene or few layer graphene, and then they act really differently depending on what quality they are. So Andy, next slide, please. So why it is so wonderful material? Graphene, when it's monolayer graphene, it has got really incredible properties. So it is 100 times more electrically conductive than copper wire. So copper wire is like what we are using in like our ordinary electrical wiring. So this is 100 times conductive then. So I'll show you like a very simple demonstration. Obviously my one will not be exactly graphene. It will be few layer graphene or maybe graphite. So if I can, like I've got a battery and the LED here. If I can make a electrical conductive line, only then this LED light will power up, isn't it? So I've made a conductive line, and I'll make it connection better. Yeah. I don't know if you can see it. It's lighting up, so I'll just make the area dark. it's lighting up because it has made a conductive line out of that graphene. So you can make your own conductive track by using only the pencil. And also it's the thinnest material. If you can go down to 1 atom thickness, graphene is the thinnest material, and it is 20 times stronger than steel. So you can see from the picture, it would take an elephant to balance on a piece of pencil to cut through a sheet of graphene, which is only paper thick. So that's how strong the graphene is. It is 200 times stronger than steel, and it's also super light. You can see from the image that a hydrogel, graphene hydrogel, is almost kind of floating on a feather-like thing. So that's how light it is, and also is very good heat conductive as well. So in that photo, you can see a very blunt piece of graphene, which is like it's very blunt, but it is so thermally conductive that without using any source of heating, he's just cutting that piece of ice just using that knife, and the source of temperature is only from the body heat. So that's how heat conductive it is. Can I go to the next slide, please? So since Andrei Geim and Kostrin Novoselov have isolated the graphene, there has been lots of research going on everywhere, and researchers have developed quite few methods to isolate the graphene. So one of them is chemical vapor deposition. You can see from the first photo, that's called CVD method. That actually does is in a closed chamber, a very high temperature will be applied to a gas that contains carbon in it, and then the graphene flake will be growing on a metal substrate, which is often copper. So that is a very good method to make graphene, but it makes a very good quality, almost like a purest graphene in that way, but the yield is very, very low, and that's why it's very expensive, and you need like expensive instrument and all the facilities. So if you want to make it in a, if you want to take it in a manufacturing stage, you need to have like a high yield. So the other methods are more suitable for the application purpose, like what we do here in our lab. So one of them is electrochemical exfoliation. So you have a graphite rod and you have some electrolyte, and as you do the electrochemical exfoliating process, all the graphene you get in your electrolyte solvent. That's one method. And another one is graphene oxide route. So from the piece of graphite, because graphene, the problem with graphene is it's not very easily soluble in any kind of solvent. They just get deposited and stack with each other. So this process does is like you have a piece of graphite, then you make graphite oxide out of it, and then you separate the flakes and it becomes graphene oxide. So with this graphene oxide, then you can have like a different kind of reduction process. It can be thermal reduction, electrochemical reduction, chemical reduction, different type of reduction, and then you end up with some graphene in dispersion. So these are called reduced graphene oxide, and depending on what reduction method you use, you get different quality of graphene this way. And another way of doing it, so these are top-down process. That means from a graphite you make graphene. And the first one was bottom-up process, so you grow it. So the liquid exfoliation process is, you can do it in several ways. So the main idea is it's like a physical process, more like what I've showed you here. So they exfoliate it, they like separate the layers physically. So we have here So this is the sonication bath. You put graphite here, graphite powders actually we do in a solvent, and as you run the sonication, then the ultrasonic wave will make them separated, and that's what it does. And this is a shear mixture, so rotating blades will be rotating in high speed, and that's how the graphite in a solvent, they will get separated. So these are the main exfoliation methods what's commonly used in researchers community at the moment. So and the next slide please. Yep, so now I'd like you to think about what would you invent or what would you create out of graphene. So if you just think about the incredible properties of graphene, you have got these great properties. What application you could have. I'm just giving you this task because I think you are the best persons who can think out of the box. Yeah, because you know, as you more know about a topic, you tend to rely on your memory and stick what has worked before, and you don't try really new things. So I think you will be the best person because as you just got to know graphene and you know the properties, I think you'd be the best person. So I'd like to give you all some few minutes, 3 to 4 minutes to think and come up with some ideas what you think. Andy, can you please put the slide before, which has got the properties of graphene? Yes, this one. So it has got electrical conductivity, thermal conductivity, super lightweight, very strong. Then if you think about an application, that would be great. Then I'll come back with what we have made and what we are working on.
So Rachel, we think you said using it in cables across the country, a bit like sort of power cables.
That's right, yeah.
Yeah.
Yeah, so a light and conductive.
Yeah, that's fantastic. Yeah, because it's lightweight and highly conductive, and yeah, that's a great idea, really. Yes.
And planes as well, because again, light and strong. And planes, and that would reduce all consumption.
What is it, Andy? Did you hear it clearly?
We didn't quite catch that. Say that again, Rachel.
Shall I type it in the chat? If you want to put the chat up, I'll type it. It's probably...
Yeah, probably.
Yeah, okay, we've got the type up.
Yeah.
It's the chat. Where? That. Okay, right.
Yeah, I can't say it.
No, I'll tell you what it is. Okay, so in the chat we've got it coming up is saying planes light to reduce fuel consumption.
Yes, that's really great. It looks like clever minds think alike. Well, we are really working on some of the similar projects. I'll be telling all about it very soon. So yeah, let me hear about some more ideas. It's excellent.
Okay.
Thank
and
you.
Another idea would be heat sinks for computers, which would make them more compact.
Yes, it's really great because like you can make very fine devices out of graphene because it's really tiny and so powerful, and for compact computers that will, I think, work really, really great. Yeah. That's great. I think I can see some great scientists growing in that Backwell School. That's really great.
Charlotte, a question here. Does it come off a surface?
It depends on how you stick to them. So my work is like a lot of my work is sticking them onto textile surface. So it doesn't always stick. So we do some surface engineering to stick on it. So yeah, there are ways to make it stick, and like for different kind of composite structures as well, you can do some plasma treatment or other treatments to make it stick. So yeah, although even when it doesn't like how it works, like hydrophobic or hydrophilic, you can work around it and make it stick. So yeah, it's not always a problem.
Clothes was one suggestion, as it would help to keep cool.
Yes, yeah, that's nice. Great idea, yeah.
Okay, well, it sounds like we've got some really good ideas there.
Yeah.
We got, looks like there's one, and also car brakes. Any thoughts on that one?
Car brakes, how would that work? Yeah.
I'm guessing you're thinking of the brake pads, but yeah.
Yeah, maybe for getting rid of the heat as you do it fast. Yeah, for switches.
Yeah,
heat dissipation. Yes, that's correct. That's correct. Yeah, thank you very much. Thanks. Great ideas, really. I'm really surprised to and really feeling excited. And some of the ideas really match with what we are doing, really. So I'll show you now what we have been working on. Andy, can you put the next slide, please? So one of our work is de-icing surface. So we have done some research on de-icing. So if you have traveled abroad, probably you have seen like before aeroplane flies, a truck comes with some chemicals, and they spray some aerosols over the wings to get rid of the ice what accumulates on the wings. So that's usually done before the flight, and I think it would be better if you can stop the ice from forming when you're really flying, because that what happens like as a helicopter or aeroplane is flying in a very high level, then all the ice accumulates. So we have made some composites what works as a de-icing device. So as the plane is flying, the ice will not accumulate on the surface. And yeah, someone was telling about the aeroplane ideas, and we work in that area. We make some graphene-based composite, and the idea is because it's very lightweight, and that's why the consumption of fuel will be low if we can make the aeroplane light. That's why we use graphene, and also it is very strong. So if you can make an aeroplane very strong but very lightweight, that is incredible. And that's why we are working on some graphene-based composites. And also we have done some work how to make it really green, environmental friendly. So we have made some graphene-based composites by using jute fiber. I've sent you some samples of that graphene reinforced jute fiber composites. These are like biodegradable, so we use the bioresins on them. So also, if you want to use the electrical conductivity property, you can make some smart composite as well. So there can be different kind of sensors on that composite, and you can use it on like a smart car, which will have all the smart sensors, or maybe solar panels on it. So we have our very talented PhD student, Marzia. She will show you one of her work she is doing with the heating surface. Marzia, would you please show us?
I'm Marzia Dulal and joined in the CFPR lab in the last September Ataman. I have awarded as a Commonwealth Scholar and joined this lab, which is very prestigious to me. Today I can show you the composite, which was explained by our Miss Shaila. The composite you are showing that it's graphene based. Yeah. For the thermo electrochemical characterization, we use this thermo imager, by which we can apply the external voltage here through this composite. When we apply voltage here, the current generates and we can measure the temperature by this thermo camera. I can show you this by applying a voltage. I'm applying 5 volts here. Look, here is 5 volt I have applied, and the current generate. The current is 0.108 ampere here. With the current passing, look, you can show there the temperature is increasing. The room temperature was 25 degrees Celsius, and with the increasing temperature, this is now 28 with time. So when we applied external voltage here, the composite will be heated and it's act like a surface heater, which melt the snow and act as a surface heater, which melt snow, and we can use in the constructive building, aerospace. So graphene is an incredible material which act as a thermal, mechanical, and the electrical conductive material. So look, the temperature is increasing and we can see here the temperature. If I touch this, the current will come. So I cannot touch this in this, just I can show you here. Yeah, this is from my side.
Yes, that's a very lovely presentation. Thank you, Marzia. Thank you. Thanks a lot. Yes, so these are the works that we have done around the graphene-based composites, and I mainly work in the research area of wearable graphene-based textiles. So the idea is you'll wear normal clothing and you'll have some sensors printed on it, so you'll not feel like there is a bulky thing attached to your body. So there will be like simple printed patterns, electrical patterns, what will work as sensors. So I'll send you a supercapacitor. So that's how it will look like. So I can show you that's one of our work. We have made some activity monitoring device. So you can see the person have stuck a textile which is graphene printed, and as the hand is bending forward and backward, is taking all the data. So actually, if a sports person is running, and they can monitor their activity, how they're doing the performance. So and it can have so other applications, maybe like in gaming and other things. And you can also see we have made a ECG monitoring device. So that means like this one is like with a touch of a finger, but if it's like it's just a simple band on your wrist or maybe on chest, it will take the data from your body, and it can have, the good thing is like it's a continuous process. You don't have to go and see a nurse to get your heartbeat recorded. You can just, maybe you are sleeping on your bed and still your health data is being monitored. So especially I'm working on some project which is like for detection of COVID symptoms. So the idea is if a person is isolating at home, they don't need to be in contact with some medical person. All their data will be recorded. Maybe it's the temperature, maybe the oxygen saturation level and the heartbeat. These are the vital signs of detecting the COVID symptoms. So yeah, that can be done remotely, and the signal will just go to the you'll get the data on your phone, and maybe the medical person, they will get to see the data, what's happening to the patient. And while like elderly people or babies or people while they're sleeping, all the data will be collected at the same time. No, the previous one, Andy. So that's what the idea of it. And to have a garment like that, it would be great if you have a source of power to run these sensors. So that's why we will start soon a project which is solar cell based textile. So it will be like same printed on a textile garment. So as you go out, you'll collect all the energy from the sun, and it will generate energy. Maybe apart from running all these sensors, maybe you'll be able to charge your phone as well if it's strong enough. And for this energy to store and to charge and discharge this energy, you need a supercapacitor, and that's what I've sent to you. Probably you've seen. So we have another PhD student working on this supercapacitor project. So the idea is the energy we got from the solar cell, printed solar cell, will be charged and discharged from that supercapacitor. Yeah.
So we have a question here.
Yeah.
What is the capacitance of the supercapacitors?
It's still on a very, very beginning stage. He's in his second year of PhD. So probably you'll get to see in one of his publications. I can probably forward it to you if you're interested. So yeah, it's still ongoing process. We're working on it, but probably not too bad. We'll be there one day. Yeah. And also, apart from this wearable, there are other exciting areas like where you can filter the water, so maybe desaline the water, or it works as a barrier where you can stop lots of components to pass through, and you can use it for purification of water. Yeah, any question, Andy?
No, we have no further questions at the moment. So.
Yeah, and I'm sure like there will be 1,000 more ideas just roaming around the brain of like creative people like you. I'm really excited that you came up with such great ideas. That was really fascinating, and yeah, I'll be.
So we do have another question.
More, yeah.
Solar panels from graphene, are they more efficient?
At the moment it is not, but it has got some properties. Like the problem with graphene is in very fundamental physics, in a purest graphene form, you can see all the great properties, but these great properties you get only when it's a single flake graphene. But when you're making a bulk, when you're making a product out of it, it's really hard to keep that same property. So, it looks like it will take some time to make a product really that really shows that promise that graphene has. So it has got the properties, but it needs working. Lots of more research. So yeah, it's very like in a baby stage, because like 2004, it's not far enough really. People have been just started working, and so this research area is still a lot to grow, I'd say. Yeah. Yes.
So is graphene used in folding phones?
Yes. Yeah, it has got some electrical properties. So actually some of the companies, one phone company is already working on how to make folding phone, or maybe folding television as well. As the voltage applied, they can like change the color, so how the liquid quantum method works. So yeah, that's one great area. There are lots of works going on in that area.
So another question, well, not so much a question, but a statement. We gather that graphene is used in super batteries as it can be stored so much more charge.
Yeah. That's great. That's really interesting to hear about all that you're excited about it, as I am feeling the same. And yeah, and the great ideas. Thanks a lot. Thanks a lot. I'd like to finish. If you don't have any more question, I'd like to finish with. Yeah, sure.
Sorry, I turned myself off again. Yeah, we have no more questions this end, but just want to say an enormous thank you very much for your time and the presentation. Excellent.
Yeah, I really enjoyed it. Thanks a lot to all of you. Thanks for listening. I really enjoyed that. It was kind of interactive, not like I'm getting excited. I got to see some more excited people here. Not really seen it, but yeah, I felt it. I'm really excited. Thank you. Thanks a lot for inspiring me.
That's lovely. Thank you.
Thanks. Yeah.
So
Thank you.
thanks very much.
Yeah, I'm sure I'll see some great scientists from here soon. I'm very sure. You're very talented.
Yeah, they're brilliant group here, to be fair. They're really good. So.
Yeah, it's nice. I wish to see you all one day face to face when the COVID is gone.
Yep.
Nice to visit.
Hopefully we can do that at some point.
Yeah. Thanks.
Yeah, we're really nice. So thank you so much for taking the time and trouble to get all together for us.
Our pleasure. We love doing this sort of thing, and again, there may be opportunities for further talks with some of our other researchers moving forward, so we can discuss that with you.
That's fantastic. Thank you so much. Myself back.
Just before we finish, I'd like to tell a quotation from Professor Andregam, which always inspired me as well, because I couldn't be the mad scientist, but I want some of you to become the mad scientists like Professor Shanku. So that's a quotation from Andregam. He said, when one dares to try, rewards are not guaranteed, but at least it's an adventure. So yes, please do some adventures. Maybe you'll not get reward, but you will surely enjoy it. If you love science like me, you'll surely enjoy. Thanks a lot. Thank you very much.
Thank you so much.
Thank you.
Thanks.